Today's lecture is on elementary functions, but let me start with a brief review of what we've covered. So we covered two topics. We covered analytic geometry, and we covered functions, and talked a little bit about how they change. So these are the two we've covered. We come to the third topic, which is elementary functions. So we want to start with this question: what kind of functions have you seen in your other math classes? So if you think about this, hopefully you say stuff like, well, I've seen the function like f of x equals x squared, or maybe g of x equals e to the x. A little bit more complicated, h of x equals ln of x. And we could even write down a function like, well, let's call it a of x equals like cosine of x. Okay. These are four very standard typical functions. In fact, they're so standard we have a special name for them. We call these elementary functions. So there's actually four types of elementary functions. The first type is called a power function. So we have what are called power functions, and that's what we're going to focus on mainly today. And power functions look like this. We'll use f of x for our function, and it looks like x to some power. It's like x to the n, where n can be any number. So you could have x to the 2, like we do up here. You could have also x to a fractional power, like x to the 1/2, which is really the square root of x. You could even have x to a negative power, so instead of putting positive 2, let's put negative 2 here. And so that would be actually 1 over x squared. So you can have any power up here in the exponent. And that's what we mean by a power function. With these functions also, I include the constants, so you can just also have a number. So you could just have the number f of x equal to 3. I also consider that a power function. The next types of elementary functions are called exponential functions. And let's just write f, c, and s for functions. These look like, so f of x equal to, instead of having the power as the number, you have the base, so you have a to the x. And actually, let's use this class. Oops, I don't want to erase all that. I'm going to use, I'll use b. Why not? Because it's a base. So you have some number b to the x. And so you could have like 2 to the x. You could have 3 to the x. You could have 1/2 to the x. Any number raised to the x is called an exponential function. For us, we're going to focus mainly on one specific type of exponential function called the natural exponential function, which is e to the x. E is this number 2.718, blah, blah, blah. The natural number, it's sometimes called, and we'll talk a lot about it throughout the semester. The third type of elementary function are the logarithmic functions. And so these, f of x equals, and you might have something like log with some number down here, so base b of x. So a lot of times you'll see stuff like log base, let's say 10 of x. And a lot of times that's just written log of x. You could also have log to any positive number, so log base, let's say 2 of x. And then for us, of course, there's going to be one specific logarithmic function we're interested in, which is the natural logarithmic function, which is, we write ln of x. And so we'll talk a lot about this. These are connected. They're actually inverses of each other, which we'll talk about today. Let me get rid of this. So ln of x is actually, if you want to think about it and write in terms of log, this is log base e of x. We'll talk about logarithmic functions and exponential functions tomorrow. Okay, and then finally, the last type of elementary function we have, these are called trigonometric functions. And I know you've seen these before, so like f of x equal to, let's say, what you have cosine of x. Let's just write them down here. Or you could have sine of x. So you have f of x equal to cosine of x or sine of x, or you could have it equal to tan of x. Although tan of x is just sine of x divided by cosine of x. So as long as you understand the cosine function and the sine function, you can typically understand the tan function. You have all their cos also, so you have the cosecant or the secant of x. Let's do that one first. So the secant of x, the cosecant of x, and also the co-tan of x. So cot of x, the cotan. These over here, remember, this is actually 1 over cosine of x. This is 1 over sine of x. And this is the opposite of tan, so it's a flip, cosine of x over sine of x. And we'll spend a whole week almost talking about these trigonometric functions. But the first thing you want to see that there are basically 4 elementary functions, and from these 4 elementary functions, we can create all the other functions by simply adding these two. I'm out of space here. Hold on. By simply adding these these together, subtracting them, multiplying them, dividing them, and then the fourth operation is called composition. And the way I remember these 4 is I remember the first letter of each one, so P, E, L, T, which spells pelt. So power, exponential, logarithmic, and trigonometric. So let me just give you a quick example here. So if you give me 2 functions, or if you give me, well, let's take a function like this, where you've combined these. So if I take f of x equals, let's say, x squared plus cosine of x. You might say, well, that's not an elementary function. I say, yeah, it's not an elementary function, but it's the addition of 2 elementary functions. So this right here is a power function, whereas this is a trigonometric function. And if you give me another function, let's say g of x, equal to, let's do, what have we done? So let's do e to the x divided by x squared plus 1. And then again, you say, well, that's not an elementary function. And I say, yeah, it's not an elementary function, but it's composed of what? Or you can decompose it as, well, you have an exponential function on top divided by the sum of 2 power functions on the bottom. So every function you've probably seen up to this point in your mathematical career can be expressed as basically a sum, difference, a product, a quotient, or a composition of these elementary functions. And so we want to study this a bit and understand how we can take these functions apart and write them in terms of power, exponentials, logarithm, and trigonometric functions, and then work with adding, subtracting, multiplying, dividing, and composing them. So let's take a look at an example. And I don't do a lot of the addition, subtraction, multiplication, and division in lecture. You'll do some on the homework in class. But I do a lot of composition, because composition is what you guys usually have trouble with. So the addition, subtraction, multiplication, division, this one's pretty simple once you get the hang of it. But the composition's a little bit tough because you're not used to composing things. And when I say composing things, that means putting one function inside of another function. So as an example, if I write down the cosine of x squared, this is a composition of power function with a trigonometric function. Inside the trigonometric function, I have a power function. So this is actually a composition of 2 elementary functions. And so let's look down here so you can see how this works. And this is the notation. You have f composed with g of 9. And what this says basically is f of g of 9. So I like to write down first what it says, then I do what it says. So it says first, can you find g of 9? And so that's f of, and g of 9 is easy. Wherever I see an x, I put a 9. So f of the square root, 9 minus 5. And so that's equal to f of the square root of 4, which equals f of 2. And so I had to get here, and I reread it. So what does f of 2 mean? It says wherever I see an x here, I replace it with 2. And so that's equal to 2 squared plus 1, which equals 5. Down here, it's a little bit different. Instead of plugging in a number, you're going to be plugging in x. So you're going to find a new function. And so on this one, though, you do the same way. F of g of x. That's what it says to do. And now this says, let's flip colors here. Write down g of x. So that's f of the square root of x minus 5. And now this basically says wherever you see an x in here, replace it with this. All right, so here, there's an x there. So I take these two circle blob things, and I basically just swap them out. So this is going to be equal to the square root of x minus 5, quantity squared, plus 1. So I just take this circle thing and replace it with that circle thing. And then when you square the square root, it goes away. So you get x minus 5 plus 1, which equals an x minus 4. Now in the next one, we're going to do g composed of f with of x. And so this is equal to, so let's write it down again. This is g of f of x. So now we're going to do the composition the other way. And what you're going to see is that you do not always get the same answer. Usually the answers are actually different. So this is what's called, the fancy way to say is that composition is a non-commutative process or operation. And so this is equal to g of, and I go and find f, and f is x squared. F is x squared plus 1. So I'll write down this right here. So x squared plus 1. And then I'll take this x squared plus 1, and I'll plug it in for the x and g. So I take this thing, because this is what it says to do, is take this thing, and wherever you see an x, you write it down. So I plug it in right there for that circle. So these circles basically just swap out. So this is going to be equal to the square root, and I just copy down wherever I see this thing, I copy down this thing. So x squared plus 1 minus 5. And so that's equal to the square root of x squared minus 4. And I'm all done. Remember, the square root does not go through addition or subtraction, so you cannot simplify this expression anymore. And that's how composition works. All right, so you know the 4 elementary functions. Hopefully you understand this idea that when you add, subtract, multiply, divide, and compose them, you get new functions, and that's where most of the functions you've seen come from. And hopefully you can kind of see what sort of a important idea this really is, because before people realized that we only had basically 4 elementary functions, people thought of these things as different. You know, trigonometric functions, sine, cosine, these were used in basically sort of surveying, figuring out the distance between objects, the height of objects. Exponential functions were used in a lot of sort of financial areas and loans, and even in navigation, although that's a long story. And then, power functions, these are used to sort of model the height of an object when you throw it up in the air, or even, gravity. But when we started putting all these things together around the 17 and 1800s, early 1800s, people realized that there are just basically these 4 functions. And if we understand these 4 functions, then we can do all kinds of sort of interesting things. We can model all sorts of interesting things. And now there are other ways to make new functions, and so that's what we want to talk about next. And like I said, I'm going to focus mostly on power functions today, and then throughout the week, in the week to come, we'll talk about the exponential, logarithmic, and trigonometric functions on their own. And so here's a couple other ways to make functions. You can actually look at the inverse of a function. That oftentimes will create a new type of function. And then you can also piece them together. So these are called piecewise defined functions. We'll look at each of these in its own turn. So let's talk about first, inverse functions and what they are. All right, so an inverse function. Okay, the idea of an inverse function is rather simple and important. The idea is if you have some number here, let's say we have 2, and you apply a function to it. Oh, let's say you take the function f of x plus 1. So you're going to add 1 to the number 2. So that's going to take you to the point 3. So you take 2, you plug it into the function, you add 1 to it, it's going to take you to 3. Of course, it would be nice if you could go back. Whenever you have a process and it's taking you some way, it's always nice to have a process that's going to take you back. And the process that takes you back, in this case, is called the inverse function. And we write it as f inverse of x. And if you think about this one's real easy. If you add 1, what's the opposite of adding 1? Well, you'd say, hopefully, subtracting 1. So the inverse of f in this case is subtracting 1. Now, not all functions have inverses. So let's look at an example where if a function that does not have an inverse, so let's keep the same number here. So here's my domain, and here's a number in it. And I'm going to apply a function, f of x, which is equal to, let's say, x squared. And that goes over here. And certainly, if you square, and let's do a different number here, so it's a little bit clearer. So let's do 3. So if you square 3, it's going to take you to 9, because that's 3 squared. And now if you go back, and you want to try to find an inverse, you'll see that there does exist a function that takes you back, and you say, well, maybe it's square root of x. But then if you think real hard, you're going to realize there's actually another function that will take you back, and that's negative square root of x. Right? Because not only does 3 go to 9, but also negative 3 goes to 9. And so that what you have here is the issue that you have 2 things over here going to 9. So the inverse is not well defined. And so we say that this function does not have an inverse. Now, if you choose one, if you limit your domain to be only, let's say, the positive stuff, so these are all the positive real numbers, then you can choose this to be your inverse. And if you limit your domain to be all the negative real numbers, then you can choose this to be your inverse. But not all functions have inverses. It's probably easier to see this if you look at the graphs of these 2 different types of functions. So this function up here, if you look at this graph, it looks just like this. Whereas if you look at the graph of x squared, it's going to look like that. And so the reason why this function on top has an inverse, or one reason we can give for it, is because when you look at one of the outputs, it goes back to just one input. And so sometimes we say that this satisfies what's the horizontal line test. Right? Horizontal line test. So if it satisfies the horizontal line test, which is not vertical, the horizontal line test, if it hits it at most once, any horizontal line you like, if it hits it at most once, then you know it has an inverse. But if it hits it more than once, like here it hits it twice, here it hits it twice, and lots of places where it hits it twice, you know that this does not, right? So no inverse. Yes, inverse. The vertical line test now, we use the vertical line test to tell if something's a function or not. So like this example here, which we've had, we know that this is not a function because the vertical line test tells us, well, it hits it more than once. It actually hits it 3 times. And the idea is if it's a function, if you put one thing in If you put something in, you can only get one thing out. Here you get 3 things out. So again, it's what we, in mathematics, we call it's not well defined. You get lots of things out, and for a function, we want to just get out one thing. All right, so hopefully this idea, this concept of inverse makes sense. And in the end, the idea is, if you step forward, you always just want to step back. So the function takes you forward. The inverse simply takes you back. Okay, so we want to determine the function has an inverse. If it does have an inverse, then find f inverse of x. So on this one, you can see that it passes the horizontal line test. If you draw a horizontal line, and it only hits it at most once. So we know, yes, f of x does have an inverse. And there are several ways to find this. One way, if you want, we could find the formula. So we want to find f inverse of x. So to find f inverse of x, suppose we should probably, I guess, find f of x. Right, so how do you find f of x? Well, this is just a line, and you see its y-intercept right here. If you look, this is 0, 2, and I'm guessing then this would be 4, so this is probably the height 5. So if you remember that y equals mx plus b form, b is 5. And then the slope, you just have to find another point here. So you go over 1 and up 2. So think about it, my change in my y over my change in my x. If I go over 1, I go up 2. So my slope is just equal to 2. So this should be y equals 2x plus 5. And we can write it down like this. And then to find the inverse, it's really simple. You just, in some sense, flip out x and y and solve for y. So to find the inverse, I'm going to, wherever I see a y, I'll put an x. Where I see an x, I'll put a y. And this will find the inverse of f. So then I solve this for y. So I get x minus 5 equals 2y. Divide both sides by 2. So I'm going to get y equals x minus 5 divided by 2. Or I could be a little bit more fancy and write f inverse of x is going to equal 1/2 x minus 5/2. I can give that 2 to each of these. And that's my answer. So if you give me a graph of a function, I certainly can find its formula if it's a line. And once I find the formula for a line, I can find its inverse by switching out x and y and solving for y. All right, so the next thing we want to talk about are these piecewise defined functions. So this is another way we can create new functions by piecing the other ones together. So the idea is probably most commonly used in the absolute value function. So if you have the absolute value of x, everybody knows how this works, but the way that it's defined seems complicated at first, but after you kind of used to it, it's sort of obvious. But everybody knows if you take the absolute value, say, of -6, that's going to be what? Well, absolute value makes everything positive, so it's just going to be +6. Whereas if it's already positive, it just leaves it alone as 6. And so the definition of the absolute value, it's piecewise defined. And when you do a piecewise defined function, you draw this large curly bracket, and you have pieces usually. And for absolute value, the pieces are if x is less than 0 versus you do something else if x is bigger than or equal to 0. So when x is negative, like in this case, when you have -6, we know that you just make it positive. So how do you turn a negative number into a positive number? Well, one way is you put another negative sign in front of it. And that's all you do in the definition here. If x is negative, then just put a negative sign in front of it, and it'll turn it positive. So absolute value of x is actually -x if x is less than 0, because you can see here, if you put a negative in front of -6x, you get +6. And if it's positive, so if x is positive, bigger or equal to 0, and then you're just going to get x. So if x is positive, like in this case, x is 6, you just write down the number 6. So you just copy down what you see. And so this is the most common use in mathematics of a piecewise defined function. You should know what the graph looks like because we'll use this graph later as an example of a function that is not differentiable everywhere. And so the graph looks like a V. Right, there are some standard graphs, everybody in this course should be familiar with. One, of course, is a line, y equals x. Everybody should kind of know. In fact, everybody should know how to graph almost any line. A parabola, you should know how, this is basically the parabola, y equals x squared. There are a couple other power functions you should be familiar with. You should know this one. This is the graph of y equals x cubed. And also the square root of x is a good one for you guys to know. This is the graph y equals square root of x. And then one last graph that tends to pop up a lot in various courses is y equals 1 over x, which tends to look like this. And you can use your calculator to check these, but you should have some of these should be sort of familiar to you, sort of like your multiplication tables. You don't need to know what 15 times 17 is, but knowing 5 times 5 is 25 will help you out a lot later on. So these are sort of the standard power functions, graphs of power functions you should be familiar with, along with the absolute value of x at this point. We'll talk about exponential functions, later on, and trigonometric functions later on. Let's do an example, one more example with these piecewise defined functions. Realize we call them piecewise defined because we define them on pieces. It's like a cut and paste job of functions. So what we want to do is determine the formula for the functions below. So first, when you look at this, hopefully you see it's comprised not of just one piece and not two pieces, but there are actually how many pieces? And hopefully you say 3 pieces. So when we define this thing, f of x, we write down the formula, there's going to be 3 different pieces. So not just 2 like last time, we'll have 3. And the pieces, you can see this here, the first piece is going to go all the way out here to -1. And then the second piece is going to go from -1 to 2. And then the third piece is going to go from 2 all the way to the right. So I can write that down ahead of time. So I know that if x is less than or equal to, let's say, -1, I do this. And then I can do -1 less than x, less than or equal to 2. That's the middle piece. And then if x is bigger than 2, I do something else. So if I'm in this green piece, I do something else. Now there is a question whether you put less than or equal here or less than or equal here. It does not matter since they have the same height. You can choose either one. But there are 3 distinct cases. And you have to put less than here or greater than here and less than equal here because there's actually a jump here, so the values aren't the same. So that does matter. Okay, so for the first one, some of these are easy. Like this one's actually really easy because it's a constant height, and my guess it's some nice number. The height's a nice number between 2 and 4, so I bet you it's 3. So if you have a value, an x value bigger than 2, the height is going to be 3. That's what this says. And then in between, this is a parabola, and I'm guessing that, we haven't studied a lot about parabolas here, so it's probably a pretty easy one. I notice, if I put in -1, it looks like I get out 1. If I plug in 1, it looks like I get out 1. If I plug in 2, it looks like I get out 4, so I bet you it's just a nice, easy parabola of x squared. That seems to work. If you plug in 0, you get out 0. And then the last one, the one on the far left here, this one's a little tricky, so I'm going to need a couple points here. So I know that this is the point. It looks like 1, 1, and it looks like it passes through this point right here, which is the point -2, 0. And I can find the equation of that line by using the fact that I can figure out the slope. So let's just figure out the slope real quickly. So m is going to be equal to, and if you go over 1, it looks like you go up 1, so it looks like the slope is just equal to 1. I don't know why I have two equal signs there. So let's get rid of that. So it looks like the slope is just equal to 1. And you can calculate it if you want, the change in y or the change of x. The x changes by 1, the y changes by 1. So it looks like the slope is 1. And you can take either point. I'm going to take this point, negative 2, 0, and I'm just going to plug it into this y minus y1 equals m times x minus x sub 1 form. And there may be an easier way to do this. I just always like to do the problems the same way. And then when I feel really comfortable, I can do it whatever way I like. And I can always fall back on this method, this technique, if I'm in doubt. So I have y minus, and there's a 0 here, is equal to, the slope was 1, times x minus, and my x input there is, negative 2. And so I'm going to get y equal to x plus 2. And so up here, this is actually then x plus 2 if x is less than or equal to negative 1. And you can check this. If you plug in negative 1 for this, oh yeah, you get out 1. It looks good. And if you plug in negative 2, you get out 0. That's good. So this is my answer. So I hope you understand what this formula means. It means basically if this is the case, do that. If this is the case, do that. And if this is the case, do that. We use this in our own tax system. If I make this much money, I pay such and such in tax. If I make this much money, I have to pay this much in tax. We call these tax brackets, where the brackets would be defined somehow. It's a little bit more complex than how I'm saying, but in a way like this. If you're here, you pay this. If you're here, you pay that. If you're here, you pay that, and so on. That's a nice, easy way to define new functions using the older functions we have. Okay. Last topic for the day are even and odd functions. So when you have some functions are special and we call them even, some other functions are special and we call them odd. What these functions do is they give us some sort of symmetry to work with, which sometimes simplifies a problem. It sort of cuts our workload maybe in half or a fourth or something, so we don't have to work so hard in solving a problem. So they're kind of useful. An even function. So what's an even function? So a function is said to be even if it basically, and here's what I think. In my head, I sort of have a model. It's sort of like, if you think of a chair, I sort of have this idea of a chair in my head, and you can show me any chair, and I know it's a chair. It sort of functions, has the same properties of a chair. So when I think of an even function, I typically think of the function f of x equals x squared, because that's sort of what an even function typically looks like. The idea is that it always has the same height on the right as it does on the left. And so the way we write this down, the way we define this, is that f of negative x is always equal to f of x. So no matter what you plug in, if you plug in, let's say x is positive, it's going to have the same height if you plug in the negative of that value. And that's sort of the picture here. And so this is the definition. And one of the points to identifying or using this even or odd functions is trying to use this definition, like I talked about in the beginning of class about this quantitative literacy, being able to read something in mathematics and then being able to do it. For an odd function, a function is defined to be odd if you have this f of negative x, and let's put a negative in front of it. Oh, f of, try and figure out what's the best way to do this. And let me kind of change this a little bit, because I think it'll be better if I write, instead of I write f of x here, f of negative x. That's right, f of x is equal to f of negative x. Make sure that's real clear, right? So f of x is equal to f of negative x. And then down here, I could write the same thing. I have f of x. Instead of writing f of negative x, we'll write negative f of negative x. Because when I think of an odd function, here's what I see. X and y. I see this function right here. F of x equal to x cubed. And so the idea behind this is that you don't have the same height. Right? So over here you have a height, and you go the same distance over here. It's not the same. It's just the negative of that height. So it's like the opposite. And that's what we mean by an odd function. So it doesn't have the same height. And you can see here, it doesn't have the same height. It has the opposite, the negative of that height. Let's take a look at some examples of how we can use this. So we want to determine, we have f of x equal to x and g of x equal to absolute value of x. Determine if the function is even, odd, or neither. So let's look at this first function right here. We have f, and that says times g of x, and so that's actually equal to then f of x. It says take f of x times g of x, which equals x times the absolute value of x. And we want to determine if this is even, odd, or neither. So the way we're going to look at this is we're going to test each case. So first we'll test a case if it's even. And if it's even, what do we know? Well, we know f of x should be equal to f of negative x. And so we're going to look at this idea, f of negative x. Now, the hard thing here is that this f and this f are not the same. And so maybe it would be more beneficial if I wrote here instead of f, you just wrote maybe, let's say, h, because we're not using h in this problem. So h of x is equal to h of negative x, where h of x is equal to this function. And so what we're going to do is we just say to ourselves, okay, well, let's find out. Let's see what h of negative x would be equal to. Well, h of negative x, wherever I see an x, I put a negative x. So I have negative x times the absolute value of negative x, which equals negative x. And if you multiply by the absolute value of negative x, well, the absolute value of negative x, what happens to the negative? Well, you can just drop it off because absolute value makes it positive. So you can just say that's the same as absolute value of x. Now, that's not equal to h of x. Right, because what's h of x equal to? It's equal to this. So these two things are obviously not equal. But if you think of the next step, once you test it's even, right? So it's not even. Then you want to test if it's odd. And so if it's odd, what you're going to do is you want to figure out, is your function h of x equal to negative h of negative x? All right. And so you're going to do exactly the same thing you did above, but instead of having a plus sign here, which we don't write, you're going to write a negative sign. So you look at negative h of negative x. And so that will equal, and you can just redo the steps, except you have a negative on the outside now. Negative of negative x, absolute value negative x, is equal to negative, and then you have negative x. And then, of course, the absolute value, you can just drop off that negative sign in there. The absolute value doesn't care about that. And then that's equal to a negative is a positive, so you get x, absolute value of x. And these two things, whereas they weren't equal here, they are equal here. Right? X absolute value of x, x absolute value of x. So you get it equal to h of x in the end. So this must be an odd function. So odd. Yes. Odd function. Okay. Let's take a look at part B and try it. So on part B, we have f composed with g of x. This says take f of g of x, which is equal to f of, and I go up and I find g of x, which is just the absolute value of x, so that's absolute value of x, which equals, well, f of x is just x, so this is just equal to absolute value of x. Oh, great. And I know the graph of absolute value of x, so I don't really have to use a definition. I can actually use a picture on this one if I want to. And I look at the picture, and it's a V. Right, that should be a V. It's hard to draw on this tablet, but that's a V. And you see that the height on the right is exactly the same as the height on the left for each input. And so that means that this is not an odd function, but this is an even function. Now there are other ways to go about this. Like in part A, This is probably the longest way I could do this. You could also plug in numbers here. You could look at, what is f times g of the number, I don't know, 2 versus f times g when you plug in -2. And you'll see here, if you do this, you're going to get 2 times the absolute value of 2, which equals 4. And this is going to be -2 times the absolute value of -2, which is going to be equal to -4. So this immediately tells me that it's not even, and it tells me that possibly it is odd. You need to check all cases to determine if it's odd, but it definitely eliminates the case of whether it's going to be even or not, and it does lead to further proof that it is an odd function. So that was for part A. Okay, so the last thing we're going to do, this is going to be homework. I'll hand out at the end of class, and the idea is you should be able to start to take functions apart and write them in their sort of elementary pieces. And so here you want to determine how to construct the functions given on the handout using only elementary functions and the operations of addition, subtraction, multiplication, division, and composition. And so when you look at this, you need to start sort of focusing on what are the elementary functions, what are the basic parts, and how are they put together. So when I see this, I actually see 3 parts. I see an x, an ln function, and a square root of x function. And so what you would do is you'd say, okay, let's make my first function the x function, my next function, and these are all elementary functions, the ln of x function, and then c of x, the square root of x. And then I can make f of x by doing what? Well, I can take a of x, and I simply multiply it by, so we just multiply it by, the ln function, so I'm going to multiply it by b, and now this is ln of square root of x, so that's b composed with c, and that's of x. So these two things are exactly the same. When you take b composed with c, I mean, hopefully you see this, or if not, you're starting to see it. When you take b composed with c, you take this and plug it in right there. So this right here is exactly that, whereas this right here is exactly this. And of course, you're multiplying, and so I put a dot there so you can see that I'm actually multiplying those two things. And you're going to practice this on a handout I'm going to give you in class.